Thank you very much for the introduction. I won't repeat the title bits, it's all on the screen anyway. Most people here probably know me as Bok though, so feel free to call me that. There are a bunch of Robs and Rogers and Rods and a few other things at work, so it's just easier with Bok. So yeah, I've been doing iOS since 2009. The very first thing I did in Objective-C was try to write an NSXML parser delegate with manual memory management, so that was quite the baptism of fire back in those days. Fortunately, I don't have to do that anymore. I'm also, just a quick plug, one of the organisers of Melbourne Cocoa Heads. Thanks for everybody that came along last night, it was really good. If you're not from Melbourne or you haven't been to a Cocoa Heads before, you can see the banner over on the right-hand side there with the QR code to help find your local community. It's a really great way to connect and meet people who are also doing the same sort of work that we do. All right, so that's me out of the way. Let's get into what we're going to talk about. So this is really broken up into two bits, and hopefully I leave enough time for the main demo. Should be about 10 minutes or so for that. But we'll go through a brief introduction on what tracing and OpenTelemetry is. And then I ordered a dozen fresh Apple Pencil Pros to appease the Apple demo gods, so fingers crossed my demo works. I've already had my heart attack when the simulator wouldn't boot 5 minutes ago, so that should be good, right? We should be good. So let's get straight into the nitty-gritty. What is distributed tracing? Or what is tracing really in general? You've probably all seen something that looks a lot like this, usually coming out of your Xcode console. Chances are that your code base is littered with print statements or NSLog statements or logger calls, depending on where you are with your different Apple frameworks and their life cycle. You might also be sending something like this to your backend. There's a bunch of different ways you can do that. But it's all pretty basic stuff. Like in this example, there's a couple of analytics, some API calls, some database stuff that's going on. Really enough to try and understand what our application is doing when we can't see the UI ourselves. The next step you might try to do here is a move towards structured logging. Now, if you're using something like SwiftLog as a package already, you can do this now by passing in additional metadata as key value pairs to your log message. And that gets attached to each log message that goes through. Structured logging is actually really useful already by itself. So especially if you're sending this off device to somewhere that you can ingest and process. You get all that extra information that's queryable. You can start to build graphs from that. You can start to build alerts on values that are coming through. You can actually start to make use of the logs beyond just plain support and triage. But there's no real relationship between these. So you can look at the log lines and you can see that the API call to /transfer is because somebody tapped on the transfer button on the line before. So that's pretty straightforward. But when you're looking at tens of thousands of these log messages across thousands of users, making that association is not so straightforward. And you may already be doing this today. Like especially if you've got your front-end data in one system, like a New Relic or Dynatrace or something, and you've got your back-end data in a different system, there's chances are you're finding in one and then trying to manually correspond it or correlate it to the one in the other to try and figure out what went wrong. So what if we were to add some relational information to this? So let's just clear this off a little bit so we've got some room. Most obvious thing is let's add a unique ID for each of these rows. Typically this is a UUID or something similar, but nothing looks as good as pasting UUIDs all over your slides. That's quite big as well. So for this one, I just put some numbers with some colors so we can easily do the correlation ourselves. But let's just pretend that they're appropriately unique and random and all of that sort of stuff. So if we've got that, we can easily add a relationship to these. And this again provides a whole bunch more information that we can start to query on top of. So this is just a parent reference, but you can see then that we've got log evidence that says the call to /transfer was related directly to tapping the transfer button for this specific user. And you've got that correlation automatically. There's no guesswork there. You can see then that we then called to grab some transactions after we made the transfer, so we can update our local cache. And that triggered a call to insert transactions, which triggered a call to refresh the screen, all of that sort of stuff. That information is available there. And if you're sending this to your log ingestion platform, you can start to query that too. So you can query for ID2 and you can see everything that happened underneath ID2 without doing any extra work. But let's just change how we're representing this a little bit. And we'll put those names back in so I know what I'm talking to. So this is a trace, or more specifically, it's a timeline representation of a trace. To run through this one last time, you can see when we tap the transfer button, it makes a call to the post/transfer, which then uses the result of that to call to get the transactions, which then inserts it into the database, which queries a screen refresh, and then finally we show the screen at the end. Now just this already, you can see which part of your queries take the longest. For this particular trace, you can start to get all of that sort of view that's there. You can see the dependencies, you can see the order of operations. You can actually probably picture in your mind how this function might look just from that. But this is a talk about distributed tracing, and going just this far is great, but we can take it further. And the key bit of distributed tracing isn't that your tracing database is distributed across multiple cloud providers, is highly available, all of that sort of stuff, is that we can cross those system boundaries in your traces by propagating it through to the backend. A bit like this. So if your backend systems also support tracing, and we are able to pass the trace information across the system boundary to the backend, and they all log to the same place, then your trace includes everything from the user tapping on that user interface item all the way through your backend systems, every single thing that's a result of that call. And that's when it really starts to get quite powerful. And that's where OpenTelemetry comes in. And it started the same place that all of these things start. It starts as a twinkle in an engineer's eye, because it's funny how much engineers like writing specs more than they like promoting other people's specs. Like, where's the glory in doing that? OpenTelemetry is a little bit different, though, in that it was the major industry players got together to do this properly, rather than trying to outcompete each other, because there's a bunch of different proprietary standards or varying levels of openness in this space. But this one is quite well supported. There's 68 major vendors at time of writing that support OpenTelemetry, so every player you've heard of. But also, because it is an open standard, there are 17 different open source offerings with varying levels of free capabilities that are available to this. So you're no longer beholden to your vendor. Say you don't like your vendor anymore, a new shiny vendor comes along, switch over where you're sending your data to. You can even run OpenTelemetry Collector, which is kind of like a proxy for telemetry data, and send it to multiple, if you like. If you want to send, you've got this Rolls-Royce SRE stamped SLO management platform. I'm not sure how many more acronyms I could fit in that. But it costs $1 million a day. You can send the important information there, the summaries, and then send everything else that you might need to your little dinky open source collection point or to an S3 bucket or wherever you want, right? Data is yours, you do what you want with it. So let's get into what OpenTelemetry is. How am I doing for time? Pretty good. OTel, I'm going to just say OTel now because OpenTelemetry takes too long. OTel includes three main types of signals. Traces and logging we've covered off already. Metrics is, you're probably all familiar with metrics, screen load times, app launch times, number of crashes, all of that sort of stuff. Apple provides a great deal of metrics to you already via Metric Kit. So if you actually hook Metric Kit up to your OTel exporter, you get all of that data in your backend for free, basically, too, straight from Apple, which is very good. But we're here to talk about traces, not metrics, so let's go a little bit deeper on that. We already covered off what a trace was before, but in OTel parlance, a trace is really a series of spans, which is pretty much corresponding to the log that we had before. Each of those spans corresponds to one of the boxes that we had on the screen, but also each row in this timeline diagram that I've got on the screenshot there. Spans also have a unique identifier that's consistent across the whole trace, so that's how we correlate things back together that way. On the span side of things, each span has a few bits and pieces, but they're effectively a named block of code, right? Pretty close to a function in terms of how we do that. They include the name, they include the time, the start and stop time of the span, usually measured in nanoseconds, as well as any other attributes you might want to include. So for the example on the right here, this is the span that threw an error. So you can see we've captured the contents of that error in the exception.message and the exception.type things. And I'm sure everybody in the room recognizes a JSON decoding error when they see one. Not triggering at all. The other important things is that span holds some context, right? That context is the unique trace identifier, as well as a unique identifier for the span itself. And that is how we get that relational thing down. When you start a span inside another span, you pass that context down, it sets a reference to the parent, all of that metadata goes to your backend. And then there's one last bit to talk about before we get in to actually looking at some code. So when we cross system boundaries, they call it propagation, like calling an API, making a database call, anything like that. We need to propagate that span context to the remote system. So for HTTP in particular, they make use of the W3C trace context spec, which says we need to pass a trace parent header. As you can see in the example, it's really basic. It's got the version number at the front, so 00 to start with, the unique hex-encoded trace ID, the unique hex-encoded span ID, and any flags that you might want to say how the span was produced. That server then can pass that trace header, recreate the span context, and use it to create any child spans that it needs on the far end. All right, so we are very close to the code, but just wanted to go through how you get this into your code base, right? What are the tools that are available? How do you start using it? Unfortunately, this is still very early days for OTel for mobile. The libraries that you can get for your backend languages are a lot more mature here, surprising probably no one, given that's their focus. But you can use it in mobile. There's just a few hoops that we need to be aware of to do that. The first one is, do not use the official OpenTelemetry Swift SDK, and I cannot emphasize this enough. I'm not sure if legitimately they got ChatGPT or Gemini or whatever to port the Java SDK over, but that's how it looks. It's the sort of code that would give a Swift API designer some nightmares. Like, it's really bad. So don't touch that. Better option here is that Apple actually provides a bunch of frameworks already. These are targeted at Swift on server users though, not for mobile, but they're functional on mobile. You just have to add the missing bits like, flushing data through when your app goes into the background and all of that sort of stuff that's not there. So they provide the three, Swift distributed tracing, Swift metrics, Swift logging. They all work the same way, but you'll notice that none of those say OpenTelemetry in the name anywhere. And that's because they don't conform to the OTel spec. That's not their stated goal, is to conform to that. Their stated goal is to be flexible and support multiple different specifications for telemetry and other things. So really, it's just a series of protocols and a way of bootstrapping them with an instrument, and that instrument can then conform to the OTel spec or whatever other distributed tracing spec you might want to go with. I think like Prometheus for metrics and a few other ones like that. So there's a library that they recommend for hooking into OTel, and that's the OTel Swift library as well. All right, some code. So to start a trace with Swift distributed tracing, you just need to call the withSpan function, which supports all the different closure flavors and overrides that you might like to use in your Swift code. In this case, we're simulating some important stuff, but it will pass through the do important thing span to the backend, and it will take approximately 10 seconds in terms of duration, and that's all the metadata that would come through on that one. You can also add in any attributes that you want, and the OTel spec includes what they call semantic conventions on this, which provide a very good guide for what you should include for very common operations, like making an API call. So for this one, you can see this is a function that will call a backend post to a backend API. You'll call withSpan with the post and then the path name that you're calling, and then we set the method, scheme, host, target attributes. There's a whole bunch more attributes in the spec that wouldn't fit nicely on a slide. But those attributes there are already enough for you to start grouping and querying and do everything else you need on the backend already. So you might be wondering at this point, should I just make one span for one function? And the answer is sometimes. Like, while it's often a good correlation, doesn't necessarily mean that that's the best idea. Like, you might start out with one for one, but if then you refactor your method to be more testable, split things off into extensions on a string, for example, that probably doesn't make as much sense as a span. as an API call method, high-level API call method would. So there's a line you need to draw there. That's different for everybody. But remember that too much data is just as bad as not enough data. Like you just have, if you have to filter through the noise, then that's not helpful for anybody. That said, I just did want to call this out quickly before we get into the demo. Because functions span get along so well, there is some niceties coming up very soon. SE415 has just gone back into second round of review. I think it was earlier this week. And it'll provide support for function body macros. So you can just attach the macro to your function, just like that. And anybody that calls that function will send through a span automatically. All right, demo time. How am I doing for time? Actually, not too bad. So before I jump into demo, I want to give you an idea of what the demo actually is. Otherwise, it won't make much sense. And don't worry, that won't take long at all. So we're going to introduce BlockBank. BlockBank is a brand new neobank that definitely wasn't written in 4 days. It's highly secure and performant. It's very high reputation, no security incidents yet. And we have a reputation for disruption, innovation, and trend setting. Nice. The BlockBank infrastructure is really basic. This has a server that's written in Swift. Each customer gets their own SQLite database, so there's no chance of being able to write to any other customer's database or expose other customers' details. Won't say that one. When the app starts, it opens a WebSocket connection, and then synchronizes all the data down into the client-side cache. Any changes that occur to your backend database are replicated in real time using value observation. So the client updates in real time, which means the UI updates in real time. And the point of this is that when we get into the demo, you can see the trace flowing all the way through the systems and back to the app again. So fingers crossed. All right, let's get out of that and let's get into some code. Well, let's run some code and hope the simulator boots. We'll just get that out of the way for now. I'll just leave that there. So here you can see the BlockBank UI. We definitely didn't rip off ANZ Plus. We were inspired by ANZ Plus. They won't kill me anyway. Very basic, balance, list of transactions. You can't click through on any of that just yet. What you can do, if my server is running, is my server running? Yes, my server is running. Is make a transfer. And the UI always locks up here the first time. Please don't lock up for me. I wish I knew why. There we go. So we'll make an $11 transfer. Fingers crossed that all works. And if we go back, the transfer's there. Yay, demo good. Yeah, you can clap that. That's the most nervous bit. All right, so that's that bit, right? But what I want to show is the telemetry side of things. Now, for this demo, I'm using the free tier of a service called Honeycomb. They support up to 20 million messages or events per month for free. But as I mentioned, there are open source ones available like Jaeger and Grafana and a few other ones like that. I'll talk a bit more about those later. But this is what Honeycomb looks like. I don't need to zoom in on that, do I? We can see it's got the BlockBank server data set up the top. Over the past 7 days, there's been 15,000 traces, so we're quite busy for a 4-day-old bank. You can see some out-of-the-box stuff that you get, right? So you get the 95th percentile for latency. We can see that some take longer than others, and this is all just coming through what's there. But it's not just the server that's got telemetry. We also have the app, which is going to be a lot less busy. But same thing, right? So we've got all of our data in the one system, and we can start to use that to correlate some things. Also, just to show you what's there very quickly, you can create boards from your queries. So just straight off the bat, you can see all of the API calls that are being made, 95th percentile of the duration that's there, everything that's broken down, all pretty good. Let's expand that. Get all of that detail there, as well as the most common errors. Now these are actual errors. I was not clever enough to make demo errors, but that's all right. What is that one? Oh, okay. Cool. All right, so let's have a look at the data that's there, right? So in the BockBank app, we'll start with, we'll look at the last 2 hours of data. You can see the traces that I've just made then. Let's switch over to server because that'll look more interesting. Last 2 hours. So this is all the traces that have come through that we've got. But let's drill in and see what we can find out. So we can search based on the attributes that are on the right-hand side here. So the one we probably want to do is the HTTP target. So if we go where http.target exists. So this is every API call that's there, and the count that's there. And if we add in the P95 of the duration as well, we can start to see that most of them took, 10 to 15 milliseconds with whatever that was, some million number of milliseconds. That was probably when my laptop went to sleep. That's okay. What else have I got to show? Oh yeah, so we can break it down too. So let's say we want to look at a particular API endpoint. So we go http.target again equals call to get the list of accounts. And again, narrows it down, shows you that's what's there. And if you want to recreate what I showed you in the graph before, we say anything that's got a HTTP target, so it's a HTTP span, grouped by target, and then we get that breakdown that says there were 6,000 calls to accounts, 2,000 calls to merchants, so on and so forth. My demo data actually came through pretty good. But it's not just HTTP spans that we're logging here. We are also doing database bits. So I could look at the backend database statements from what's here. No, want to make sure that we limit it to database statements, otherwise it will mess my graph up. So we can see that the most common thing is commit transaction. I mean, everything runs inside a transaction automatically, so that's to be expected. But select from account is the most common one. You can already start to get here too if you have actual, not 1 millisecond times that if a query takes 10 seconds, you'd see that showing up here. You can start to get that sort of detail out of that. And that's all out of the box. You don't have to do that. Anything you need to do is send the data to OpenTelemetry. Okay, so we have the same available for the app because the app is also doing telemetry. That's going to be a lot less because it's only the one that I've done just then. But you can see same sort of thing coming too. We're mostly doing syncs to the client side, passing all of that through. All right, so let's go and find something in particular. So if we go back to the app, we'll make another transfer of, let's say $5 this time. Transfer complete. We then go into Honeycomb and we can say run query, but for the last 10 minutes. Now, let's look at the code for this. So this is the form to make a transfer. Just a straight up Swift UI, nothing particular there. The bit that we're interested in is this bit here, the button, the transfer now button, right? What happens when we call that? We have a span here, which sends it through as tap to transfer now. All it does then is calls the payment client to make a transfer, like the transfer API, passing the source account, target account, amount. Pretty basic. But it means that we've got a span called tap transfer now that we can search for. So if we go name equals tap transfer now, let's get rid of that because that's not relevant in the last 10 minutes. So that's probably it just there. So we can click on that and go view trace. And this is the moment of truth. So this is the full journey end to end that trace has taken. We can see we've tapped the span that's there, tap transfer now. It has made the call to /transfer. And you can see on the right-hand side, API details, who you called. If it went wrong, you would obviously have that information available to you. It was a JSON request. What else is of interest of there? Probably not too much. But you can then see these two in the purple are the app, bockbank.app in the service name, and then we switch to the server side. And that's happened automatically. I haven't had to go and find the corresponding server one and figure out what went wrong with that. We can see that right there. And you can see the server-side trace for that. You can then see that we spend 300 milliseconds doing a fraud check, and that's the most of our time is spent on this API call. We can then see the database queries that it's making. So scroll back up. You can see that that's select all from accounts, where we're grabbing a particular account ID, we're grabbing another account ID. So we're probably grabbing both accounts that are involved in the transfer. And then we do some updates. This is using GRDB, so it tries to upsert as it goes. So it's trying to update and then falls back to an insert. And you can see all of that there. So we can actually go into, so you've got a pretty good idea of what that code might look like. If we actually look at it running in context, go up because it's up. No, that's not the right one. Payments repository. That's the right one. So we can see we grab the source account, we grab the target account, we do a little bit of validation, we decrement one account, we increment the balance in the other account, we create a transaction for the source, a transaction for the target, and then we write all of that to the database. And that's pretty much what you see there. So if any one of those steps fail, there'll be an error attached to it, and you know exactly what failed without having to dive in and try and figure it out yourself. But it doesn't just stop there. As I mentioned, there's a WebSocket that goes back to the client. So you can see the correlation here of where it starts to send it back to the client, because that WebSocket associates the trace all the way through. And then we're back. The client's receiving it. The client's writing that updated account into its local database. So you can see the journey end to end all the way through. If we hooked up rendering events on the client side as well, you could probably see that being the screen being re-rendered as a result of that trace. So you've got something that's happened on the client, and on one screen you can see what caused it. It was also the client, or it might have been a different client, or it could have been a backend service, or external third-party service. You can see all of that coming through. One last one then. Let's do one that fails. So if we tried to transfer $100, that's probably not the error message that I was expecting. I was probably expecting that to show, insufficient balance or something like that. So why did that happen? Let's do our query again. We can see here, this is our updated trace. You'd normally filter off the user to find the right one, all of that sort of stuff. It looks a whole lot shorter this time. We got as far as selecting the 2 accounts, but we didn't make it any further than that. If we look at the response we sent, the response we sent said insufficient funds, but that wasn't the error that we showed the client. So what happened there? Let's have a look at this one. We can see the client had a different error when it coming back from its thing, because the given data was not valid JSON. Okay, so that suggests that this is sending, can I see the HTTP response here? No, I can't. Content type for the request, but not the response. But it suggests that the response was plain text or something similar or different that wasn't JSON that we could pass, right? So we've identified what that error is. We can fix that. That took 2 minutes, if that. All right, that's basically me done. Just want to wrap up quickly. Go back to Keynote. So that's pretty much it. Hopefully that's been a helpful introduction to OpenTelemetry and distributed tracing. As I said, it's all open source. You can all go and play with it. It doesn't cost you anything to give it a go. The main thing there is bringing all of this back into your responsibility. So you don't get all of the niceties out of the box that you might get from a New Relic or a Dynatrace and their automatic swizzling of your view hierarchy and all of that sort of junk. But you can do what you want. And it's especially important for things that those services don't support, like if you have a syncing layer or if you've got other SDKs that you're working with. But one last thing to cover before we close. So just because you're adopting something that you're building yourself and it's an open standard and it's not using a proprietary vendor anymore, doesn't mean that you're exempt from the App Store review guidelines. You're still collecting user usage info, so you're still required to obtain consent and obviously stop doing that if that consent is revoked. And that's not just because Apple says so. That's being a good citizen on your iPhone and respecting your customers and their decision and not being creepy app developer. But that's it. So two QR codes on the screen there. The one on the left is the demo code that I just ran through. The whole thing is available there. Anybody can go and play with it. The one on the right is a Cocoa Heads talk I gave about 1.5 years ago now about the ANZ Plus app. If you're interested in learning more about what we did for that, that's there. And obviously, I'm at bock@mastodon.social if anybody wants to connect that way.